I am going to go over the best equations for algebra-based physics. So let's think of this kind of review. I'm not going to go over the concepts in full detail. I'm going to do it as little as possible. But this is basically my equation sheet for the second semester. That's physics. Look, I did that. Physics. Second semester. So in the second semester, you cover electric field, magnetic field, circuits, and stuff like that. And this is the algebra-based college level course. So there's any number of books you could use. They all differ slightly, but not dramatically. So let's just get right to it. The very first thing is vectors. So if I have a vector A, and there are a lot of vectors in here. So here's a vector A. I can represent that a couple ways. I can represent that as a magnitude and angle, not super useful. But if I do know the angle with respect to the x-axis theta, then I can say A is the vector AX, AY, AZ, where that's the x, y, and z component. Another way you would write that, this is the angle bracket notation, which I like. Other books do it like this. AX, x hat, that's a hat, plus AY, y hat, that's a hat, plus AZ, z hat. Then others do it like this. AX, I hat, because they're like, hey, x hat is too obviously what it is. Let's change it to I, and that's kind of cool. And I get that, but I do it this way. AY, j hat, plus AZ, k hat. And then, of course, you can find AX if the angle is measured from the x-axis is A cosine theta, AY is A sine theta. The Z you cannot find without another angle in spherical coordinates. Not going to do that. The important vector operations are the dot product. Of course, there's adding and subtracting and multiplying. There's the magnitude. I guess I should write that. The magnitude of the vector A is going to be the square root of AX squared plus AY squared plus AZ squared. The unit vector is something weird if you haven't seen this, and it actually comes out very useful. A hat, yes, it's the same hat that's there. It's going to be the vector A divided by the magnitude of the vector A. And I will show this a little bit. I think this would be an appropriate thing for algebra-based physics. It's really important for calculus-based physics. You can get by without using these unit vectors, so in most cases, but things get a little weird if you do. So then you have adding and multiplying by a scalar, but I want to focus on the dot product. So if you have A dot the vector B, that's going to give you AX BX plus AY BY plus AZ, BZ. So each of these is a scalar component, so you get a scalar. You could also write this as the magnitude of A, magnitude of B times cosine of the angle between A and B. Now, for the other very, very important vector product, there are a lot of things in this course that can only be done in 3 dimensions. So there's also this, A cross B. It's going to give you some vector C. So this uses the right-hand rule. So if I have, let's see, A cross B, let's do it like this. If I have A and B and some angle between them, theta, then the answer is going to be a vector that's perpendicular to both A and B, which is either this way out of the paper or that way into the paper, and you find it using the right-hand rule. So if I let my fingers cross in the direction of A, then B, then that gives me the direction. So C would be into the board. We draw that into the board as a vector with an X because you're looking at the back of the arrow, and so it looks like you see feathers on there. I know it's a little weird. I can find the magnitude of C as the magnitude of A times the magnitude of B times the sine of the angle between them. Okay, so that's the cross product. Okay, now let's get to electric fields and forces. Moving right along. Okay, so if I have, I'm actually going to start with electric field. A lot of places start with the Coulomb law, but I think it's better to start with electric field. If I have a point charge, and I know the vector distance to some observation location, I can find an electric field there, E. Electric field is the force per unit charge. It's just like the mass per unit, the force per unit mass for gravitational field. It's, if I did put a charge there, that's the force I would get. So it'd be F equals QE, and this is QO, a test charge, and that's Q1. So this would be the electric field due. This is electric field due to this charge. The force is the charge that I put there due to that electric field. So if I want to find the magnitude of this electric field due to a point charge, E is 1 over 4 pi epsilon naught Q1 over R squared. That's the magnitude, where 1 over 4 pi epsilon naught is a constant. Sometimes it's called K, and it's 9 times 10 to the 9th Newton meter squared per Coulomb squared. If you want to find this as a vector, you have to do things a little bit differently. In that case, I need the vector r. I need the unit vector r hat. Okay, and that's the vector from the charge to where you want to find the electric field. So a better way is this. E is 1 over 4 pi epsilon naught Q1 over the magnitude of r squared times r hat. That will give you a vector. And what's great about that is that if I have two charges, a plus and a minus, I can find, we'll call this 1 and 2. I can find the electric field right here as the vector sum. So this is E1, a vector, and this is E2 as a vector. And then I add those as a vector, it gives me the net electric field. If I want to, and then we can use that electric field to find a force for whatever we want. Okay, so there's a whole bunch of problems like that. Normally, I would like to, if in my algebra-based course, I would want to give problems where you add vectors, but in simple situations. So maybe something like this. Why am I even talking about this? A plus here makes an electric field that way. A minus there makes an electric field this way. And then you can add two perpendicular electric fields without having to get into the unit vector stuff. Okay. Oh, here's another one. If you have parallel plates, E, the magnitude of the electric field due to parallel plates is Q over epsilon naught A. That actually turns out to be very useful. If I have two plates like this, it makes a fairly constant electric field inside of it. And so this comes up a lot. You can't really, a lot of these equations you don't have the ability to derive. And it's not you, it's just that you would have to derive them with calculus, and it's an algebra-based course. So that does make things a little bit weird. Okay, moving on to electric potential. We have this from your previous semester. Work is the change in energy. That's the work energy principle, where energy could be kinetic energy or potential energy or whatever. But with that, we get the change in potential energy. This is 4E, that's a vector, constant. That's important. If the electric field is constant, then I can write delta U is negative QE, that's the force, dot dr, delta R. So that is the displacement vector from where you start to where you're going. That's the electric field, and that's the charge you're moving. This is literally the opposite of the work done, which is where you get that from. If I divide both sides by Q, I get delta V, which is delta U over Q. That's the change in potential energy per charge is the electric potential, V, in volts. And that would just be negative E dot delta R. And you can write that, since it's the dot product, you could write that as negative E delta R cosine theta. Okay, that is only true for constant electric fields. If the electric field is not constant, you cannot do that. Do not do that. Okay, so I see that mistake a lot. A lot of people say, oh, delta V is ES, and where S is the displacement. That's true if the electric field's constant, and that's why you have this electric field due to the plates. Now, if you have a point charge, I can actually find the change in electric potential going from infinity to that point, and I get this, V equals 1 over 4 pi epsilon naught Q over R. That's the potential due to a point charge with respect to infinity. That's the same constant, This is the magnitude of R, okay, and it's not squared. So this looks a lot like the electric field. It's not. It's the potential. It's a scalar value, and it's a scalar value. Oh, and it's R, not R squared. But again, if I have 2 point charges, it still obeys superposition. So if I find the potential due to that point and the potential due to that point right here, I can add them together as a scalar. It doesn't matter about direction. So that makes it a little bit easier. And one other thing that we get to with potential is capacitors. We define capacitance as Q over delta V. So if I have 2 plates and I put a charge, a positive charge Q on this one and a negative charge negative Q on that one, there'll be a potential difference due to that electric field. And the value of that potential difference depends on the parameters of the plates, which we call the capacitance. So this is a value about plates, not how much charge or potential is on there, but the configuration of the plates. And that would be in units of farads. If you have a parallel plate capacitor, you can find the capacitance for anything. But if it's a parallel plate capacitor, it would be this. Epsilon naught A over D. And notice it looks just like this, because that's that electric field that we get for the change of potential. That's the area of the plate, separation of the plate. Okay. Oh, and that can give too, you get this. If I have 2 charges, I can find the potential energy of the system, UE. It's just 1 over 4 pi epsilon naught Q1 Q2 over R. That's the potential energy stored in 2 charges near each other. Okay. There's also energy stored in this potential, these charges on a parallel plate capacitor. It would be U is 1/2 Q delta V. That's the energy stored in a parallel plate capacitor. Okay, moving on to electric circuits. Jumping around. You know, I'm not really. A lot of times these seems disjointed from what you've done before, but there is a connection to electric field. But let's just start with the definition of electric current. I is delta Q over delta T. This is how fast charge moves through something. It's coulombs per second. Okay. And we can also write this as the following. I'm trying to get it right before. N E A V D. So this is the start right here. This is the drift velocity. VD is the drift velocity. So if you look at a piece of metal and you have charges moving, this is the average speed of those charges that they move. That's the drift velocity. A is the cross-sectional area of the wire. E is the electric charge of the charge carriers, probably electrons. And N is the charge carrier density. How many charges per cubic meter? We also have this equation, very famous equation, the resistance. All this stuff, well, not all of that. All this depends on the property of the wire. So we can actually pull that together and call it resistance, and that's going to be delta V over I. So this is Ohm's law. It's kind of a big deal. It says the change of potential across a resistor depends on this thing and the current, or you could use it to define current. We have another version of like this, rho L over A. This says that if you increase the length of the wire or decrease the area, you increase resistance. Rho is the resistivity. It's a property that depends on the type of material that you have. With that, we have this equation, P equals I delta V. This is the power dissipated in a element in a circuit. That's the current, and that's the potential across that current. We have also, when we talk about circuits, we have 2 rules, the loop rule. This says that no, it's not a rule, it's a rule. This says that if you go around any circular loop in a circuit, delta V loop equals 0. Then we have the junction rule. This says that if I have current I1 coming into a junction where more wires meet, and then I2 leaving, I3 leaving, I1 equals I2 plus I3. And you can have as many wires as you want. But these two together are how you solve for all those circuit problems to find the current in a different branch or something like that. There's also the two equations for equivalent resistance. If I have resistors in series, R series is going to be R1 plus R2 plus R3 dot dot dot. You just add them up. If they're in parallel, 1 over RP for parallel is 1 over R1 plus 1 over R2 plus 1 over R3 dot dot dot. Be very careful here. A lot of people just take 1 over these, add them together, and say that's the resistor. Then you have to take the inverse. Okay. So just a reminder, things are in series if they have the same current running through them. Things are in parallel if they have the same voltage across them. Okay, circuits. Oh, there's this one. Rho equals rho 0, 1 plus alpha delta T. This tells you how the resistivity of a material changes with temperature. So this is the resistivity at some temperature T0, and then this can calculate the resistivity at a new temperature where delta T is T minus T0. So that T0 matches up with that, and alpha is the thermal coefficient. I can't remember exactly what it's called, but it depends on the type of material that you have. One of the things that you'll look at is RC circuits. They're kind of complicated, but there are two equations that a lot of classes use. The first is this. This is for a charging capacitor. This is the charge on a capacitor as a function of time. This is this is a discharging. No, yeah. This is the final charge on the capacitor. This is the the natural number E, T over RC. RC is the resistance and capacitance. If I discharge a capacitor, it looks like this. Q equals Q0, E to the negative T over RC. Okay. Magnetic fields. I'm running out of time here. So if you have a charge, it makes an electric field. If you have a moving charge, it makes a magnetic field. So the magnetic field due to a moving charge, I'm going to write the full version. Mu naught over 4 pi Q V cross R over R cubed. So this is that cross product where you have to use the right-hand rule. And this R is the vector from the charge to where you want to find the magnetic field. But the most important thing is if I have a positive charge moving out of the paper, then if I put my thumb in the direction of that, the magnetic field has a circular path around it like that. And it decreases with R. And I have R cubed down here because I have R up top. You could also see this as mu naught over 4 pi QV cross R hat over R squared. Okay, they're the same thing. You could also, it's pretty hard to calculate this in different situations because you got to know the velocity vector and the R vector. So a lot of times you could just say the magnitude. See, I don't even want to write that. Okay, but we can replace QV with IDL. If you have a very short wire, then B, just a short wire, is mu naught over 4 pi I delta L cross R over R cubed. And that's the length of the wire, and that's the current in the wire. So I guess I should say mu naught over 4 pi is 10 to the, it's 10 to the negative 7th. Yeah. And I have that as newtons per amp squared. I'm not sure if that's right. I think that's right. If I have a long wire, then I have this B, the magnitude of the magnetic field is equal to mu naught I over 2 pi R, where R is the distance from the wire to where I want to find the magnetic field. This is a scalar equation, okay? So just be very careful. You have to kind of determine the direction using the right-hand rule, okay? So there is a vector version of this, but you don't get that, in Algebra-Based. And also you can't derive this in the Algebra-Based, but there you have it. The force on a charge, FB, the force on a charge in a magnetic field is QV cross B. The force on a wire in a magnetic field is I delta L cross B. So if you know the magnetic field, this is just the force on a short little piece, but if the magnetic field's constant, you could use the whole length right there, and that's the current. The torque on a loop, tau is for torque, is mu B sine theta, where mu is the magnetic dipole moment, where mu is NIA. So that's the number of loops, the current in the loop, and the area of the loop. We have this one, B equals mu naught in I over L. This is the magnetic field in a solenoid. So N is the number of turns, and L is the length of the solenoid. So like a cylinder like this. So this would be L, and that's the number of turns. And then we have this. Oh, no. Yeah. You could also write this as mu naught N I, where this lowercase n is the turns per unit length. It's N over L. Okay. Faraday's law. I think I'm going to run out of time. So first we have this idea of magnetic flux, phi B. It's literally going to be B dot n hat A if the area and the magnetic field are constant. A lot of times they just write this as B A cosine theta. So in this case, be careful. B is a vector. A is a flat plane. So theta is the angle between a line perpendicular to area and B. So if it's the magnetic field is coming straight into the thing, theta would be 0. The magnetic flux is important for Faraday's law. This says that if you have a changing flux, you create an electric field, which creates a voltage, and we call the voltages EMF for electromotive force. It looks like this, N delta phi B over delta T. That's kind of a big deal. A lot of books will put a negative sign there, but I wouldn't. I would just use Lenz's law, which is really complicated. This says that if you have a changing flux, it will make, and it made a magnetic current. That current will make a magnetic field that would oppose the change in flux. That's a lot to handle right there. Okay, but I don't want to go through the whole thing. Okay, where are we? I want to point out there is electric flux too. I didn't put that in there because that a lot of books use electric flux when they talk about Gauss's law. But Gauss's law is just way too advanced. It doesn't make sense if you don't use calculus. I don't like it. We have this. EMF equals negative L delta I delta T. This is the change in voltage across an inductor that depends on the voltage across a conductor depending on the change in current. Then we have a bunch of electric field stuff for electromagnetic waves. This is true for an electromagnetic wave, C times B. The magnitudes are related by C, where C is the speed of light. C is 2.99 times 10 to the 8th meters per second. We have this, N equals C over V. This is the index of refraction. This is the ratio of the speed of light in a material to the speed of light in a vacuum. So that V is the speed of light in the material. We have this, I equals I0 cosine squared theta. This is for polarized light. So if I have polarized light of intensity I0, this has to be polarized. Coming into a polarizer, the intensity of light coming out would be I, and then theta is the angle between the polarization of this light and the filter. In general, I is P over A. It's the power per unit area for light. Yes, and we do reuse the same symbols. Okay, the last couple things, we have this N1 sine theta 1 into sine theta 2. This is Snell's law. This tells you the relationship of light coming into a surface. So that's theta 1 that's theta, and it bends, that's theta 2, and this is index refraction 1, index refraction 2. And then finally, we have this very commonly used equation. 1 over F is 1 over P plus 1 over Q, or 1 over I plus 1 over O, depending on how you want to do it. This is the focal length for an optical piece, either a lens or a mirror. This is the location of the image, the distance from the image, from the object to the lens, and this is the distance to the image. Now, you can have positive or negative focal lengths. I'm not going to go into that. Depending on if it's a converging lens, converging mirror, then it would be positive. If it's diverging, that'd be negative. The image and the object could be negative or positive. If you only get a negative object distance with more than one lens, the image is negative if the image is on the wrong side of where you would expect it to be. So if I have a lens and I form an image on the same side as the object, it'd be negative. But for a mirror, same side would be positive. I know that's confusing, but that's the way it works. Okay, so there's a lot of stuff there. I had one more thing that I use in my class, the Doppler shift. FO equals FS times, and this is the approximate version, 1 over V relative over C. This tells you the Fs is the frequency of light from the source, V is the relative velocity between the source and the observer, and C is the speed of light. Okay, that was longer than I wanted it to be, so I kind of rushed at the end. There's a lot of stuff there, but hopefully that helps.